Hi everyone. So I'm going to brief you about multi-component tympanometry alone. Actually, it is two parts. One is multi-component and multi-frequency. I'm going to teach you multi-component tympanometry, but then I'm going to leave you with the slides of multi-frequency, which may not be understandable, but then you have some references in that, so you can go through it. If you understand, it's well and good. If you have any doubts, you can come and ask me anytime as usual. Okay, so this is some basic principles that we had already seen. So this is going to be some recap. So immittance, which is a general term, you know that it is a combination of impedance and admittance, and notations for impedance and notations for admittance, and its definition. Okay, so the concept of impedance, this is a very basic concept that we had seen earlier. So that is force. So the force could be of static or force could be of dynamic. So in this case, so as you know, what we would be talking about, force as an dynamic force, that is like a sine wave which constantly changes. So we know that sometimes it is maximum, sometimes it is minimum. If you take an average of force which is dynamic, like especially like a sine wave, we are going to get null. So that's why we use RMS. The formula for sine wave is given there, and we know that impedance is made up of a lot of components. Okay, so major components is reactance and resistance, and stiffness and mass form the reactance component, and friction forms the resistance component. But however, as you know that none of them is separable in a single system. All the three combinedly acts in a single system. So there is no system exists in isolation, which is stiffness, mass, or friction. It could be stiffness dominated system, or a mass dominated system, or a friction dominated system. But then nevertheless there would be other components existing in that system too. Okay, so what does these three components do? As I said, the reactance mainly reacts to the input sound. The input force is a sine wave, as you know, and like how impedance in a steady force is loss of some energy, so similarly here in a dynamic force, okay, you tend to lose some amount of energy, mainly that is in terms of phase shift and also in amplitude reduction. So the amplitude reduction without changing in phase is considered as resistance, where because of which is because of friction, but the amplitude, the phase change because of the system is considered as reactance. Okay, so this picture might have been familiar. So where the force leads and lags velocity. Okay, so finally all the three reactions, that is reaction by mass, reaction by stiffness, and resistance induced impedance changes, all of them could be plotted in an impedance plot or an admittance plot. The main difference is in the notation, and they are inversely proportional to each other. Okay, so this is a rectangular plot where we are considering it as the length of the triangle, or a diagonal line which is intersecting this three-dimensional plot. You must be knowing, so we have discussed about it before. And this is an polar notation, which is the other way of representing the same impedance. Yeah, so coming to the main part, that is how to estimate an impedance. Okay, so we know that routine tympanometry, that is 226 hertz probe tone. Okay, so unless like what you have seen in a typical representative diagram, so it flows very close to the stiffness axis. Okay, so because of it, we think that the rest of the components contribution, that is the reaction, the friction component and the mass component, they are negligible. So that's why it could be written as y is equal to, so the j is an imaginary number. Okay, so bm plus bs plus g. The g is conductance, which is written in a real number, whereas rest two are written in imaginary numbers. Okay, so this is a very rough example, which it is not possible to explain impedance this way, but just for your understanding of what goes on in the measurement system, I have written like this. So in a real impedance or in a real tympanometry that we do using 226 probe tone, actually the major contribution is by the stiffness component. So I've represented it here as 90, for example, and the contribution by the rest of them is very, very negligible. So that's why we consider the total impedance as the impedance offered by the stiffness component alone. So this is why we call it as a single component tympanometry, because we are using only one component, that is the stiffness component, to measure it. Okay, so this is a way of representing how many components does exist in the assist impedance reaction. So you have some 3 components and the inverse of these 3 components, and then what you actually measure is only one, that is BS, and that is what we consider it as total admittance. The graph, the tympanogram, what you see, the tympanogram is nothing but Y total. The Y total is nothing but BS of impedance. So there comes a problem, that is, in some conditions where there is a pathological middle ear or a mass dominant middle ear or increased probe tone frequency, that is, if you use high frequency probe tone, so this assumption is violated. So that means the maximum contribution by the stiffness component doesn't exist anymore. Rather, the vector could flow somewhere like this green arrow, where there could be more contribution by the resistance and the mass component of it. In such circumstance, since these numbers are imaginary numbers, so we saw that we used notations J for representing it, I and J. Okay, so that way we cannot add these components together like these ones. So though I wrote as plus plus, but then actually it is not a numerical number to get added up just like that. So because of that reason, we cannot add these components up. So what do we do? So since they are imaginary numbers, as I said, they cannot be added. So this is one example of what could be happening in this sort of tympanogram. So where there is more contribution still by mass component, right? Okay, so but there is some amount of contribution even by stiffness and resistance, which could still make up the total impedance. But then in this case, if I am going only by the previous notation where I am just measuring the stiffness component of it, I would be measuring only this instead of representing the total admittance. So the total admittance could be 100 units, for instance. Rather, by measuring single component, I'm only reporting this much. So which is not the actual picture what goes on inside and middle ear. So that is where the multi-component and multi-frequency tympanometry comes into picture. That is, whenever these rules are violated for the normal single component tympanometry, so those things I had already mentioned. So once again, it is there in the slide. Whenever there is a mass dominated middle ear or any pathology of the middle ear which is affecting the mass component of it, rather than the stiffness component. Okay, so and increased probe tone frequency. So that is, you purposefully increase the probe tone frequency. That means maybe you wanted to measure at 678 or 1000 hertz, or maybe the child is very young. In such a case where there would be more contribution by the mass component than the stiffness component. Okay, so in any of the circumstance, what happens is there would be more contribution by rest of the component. Okay, so this picture is one of the picture which is explaining what happens to the stiffness dominant or the total reactance as we change the frequency. So this could happen due to a middle ear pathology, or could be happening due to you increase the probe tone voluntarily. Okay, so as in the example what I had quoted earlier, so at 226 hertz, there is no doubt that the total admittance flows very close to the stiffness axis. So whereas when you start increasing the probe tone, slowly the impedance vector starts flowing more towards the midline. So that means, say for example here, this is equidistance from 0, that is the equidistance from resistance and stiffness dominated. But still, what would happen when they get added up together? So that means the amount of impedance offered by the resistance and the amount of impedance offered by the mass together, they would pull these arrows towards the midline. So that's what happens here. As and when the contribution by these two components, that is the resistance and the mass, increases, this arrow gets pulled towards the midline. Okay, so and you can see that at 0 degree, where bt could be equal to 0. So that means to say the mass continues to increase in such a way that at one point of time there is equal amount of stiffness and equal amount of mass contribution towards the impedance reaction. So that would, since these two are in opposite phases, they will get cancelled out each other. Okay, so that would lead to a phenomena called resonance at this point, where the total admittance is only because of resistance, because mass and stiffness gets cancelled against each other because they are equal weightage, or they contribute to impedance reaction in the equal amount, equal quantity, but in opposite direction. Okay, so there is no contribution by the mass or stiffness, rather it would be only because of the resistance. So in that case we would call it as resonance. This quadrant we'll call it as stiffness dominant, and this quadrant we'll call it as mass dominant quadrant. And what happens when we further increase the mass contribution towards the impedance reaction, that is simply by increasing the proton frequency, what would happen is there would be more and more mass contribution towards the impedance reaction, and the impedance vector indeed crosses the 0 and start flowing in this quadrant, the negative quadrant. So that means to say in this case the contribution by mass is slightly greater than the stiffness in these two cases. Okay, so quick recap once again. As I said, it is 226 hertz would flow very close to the stiffness axis, because in the normal mid layer, or whenever you use low frequency in the normal mid layer, the contribution by mass and resistance is very less, negligible indeed. Okay, so but when you increase the proton frequency, or when there is a mid layer pathology which alters the contribution by the mass component of the middle layer, what would happen? This arrow or the impedance vector starts flowing towards the mass dominant direction. Okay, so in between it crosses one place, that is 0 degree here, or it flows on the resistance axis, where the impedance offered by mass component and stiffness components is exactly equivalent, exactly the same, but in opposite directions, so they get cancelled, and that leads to resonance. So at this point only the impedance is completely offered by, the total impedance is completely offered by the resistance. Okay. Okay, so this slide is one of the very important slide that you need to understand. So here what is depicted is the impedance vector flow as the frequency is increased. You know that. Okay, so there is something called bt. So bt is equal to, right, okay, so minus bm plus bs, excuse me for the poor handwriting. So together it is considered as bt. So they would resultant is equal to one value, so that could be, say, probably x. So similarly here, that's bt here, so you have b, so here the capital B is nothing but the bt here, what I explained. So you know that in the normal mid layer, right, in you have, just a minute, so in the normal mid layer, so you have the impedance vector flowing in this direction, which is very close to the stiffness axis. Whereas as we increase the mass, so you can see that the impedance vector starts flowing towards the 0, and then further it flows down to the mass quadrant. So we can imaginarily divide this lines, that is 45 degree, that is equidistant from 0 and 90, and similarly minus 45 degree, that is equidistant between 0 and minus 90. Yeah, okay, so In this case, as the impedance vector starts flowing from the stiffness axis, and as you increase the frequency, it starts flowing towards the mass axis, mass quadrant. In between, it has to cross this place called 0, where the impedance offered by the stiffness component and the mass component, they are absolutely equal. So Bm is minus 25, for instance, and Bs is plus 25, so they would result in net value of 0. So when it is 0, so you know that the total impedance is Bt plus G, that is the conductance, that's the total impedance, that is Y is equal to Y total is equal to Bt plus this one. Okay, so now since this Bt has become 0, so the total impedance or admittance offered by the system current now at this point, which is close to 0, is just because of the conductance and not because of the mass component or the stiffness component. So, and that is what is considered as resonance. So this is the stiffness quadrant and this is the mass quadrant, and in between you have something called resonance. Okay, so this happens as we increase the frequency, or there is a pathology which alters the middle ear in such a way that there is more contribution by the mass component of the impedance system. Okay, so then also the same thing happens. Yeah. So in the next slide, we have depicted different impedance vector quadrant flow and the resultant graph. So before that, so we have seen that this type of interpretation is considered as multi-component tympanometry. So why multi-component? Okay, so we have seen earlier, that is in this slide, right, that so we are measuring only Y total by measuring Bs. But now we know that there is some contribution by mass and there is some contribution by conductance also, or susceptance also, because of which Y total is no more just a simple representation of by Bs, rather it is a combination of all the three. So can we add it up? As I said in the previous slide, we cannot simply add it up because they are imaginary numbers and they are not real numbers. So what is the solution? We represent all of them by independent graphs. So there could be a graph for B, there could be a graph for G, or there could be a graph for stiffness reactance, mass reactance, and conductance. But in this case, we have two components, means the graph represents it by two components. One is B total, that is BA, that is the total difference between the mass, the total value of mass and stiffness combined together, and conductance. So we call this as B and G graph. We call this as B and G graph. Okay, so this is what happens to the stiffness axis, means the vector which is flowing very close to the stiffness axis. That is, this is the 45-degree angle that we saw in the earlier picture, and this is a 0 degree, and this is a mass quadrant, and this is stiffness quadrant. So when the impedance vector is flowing very close to the stiffness quadrant, that is between the plus 90 and 45-degree angle, so we can see typically a graph which is a single peaked B graph and single peaked G graph. So we call this as 1B 1G graph. What happens when the impedance or the frequency is increased to 1000 Hertz? When the frequency is increased to 1000 Hertz, what happens is the B graph starts notching, right? We will see in some time why the notch occurs. Okay, but we'll call this graphs as 3B 1G graph. So why 3B? So this is based on the extreme values. In this graph there's only one extreme value, that is the positive peak, but in this graph there is three extreme values. One is here, one is here, and one is here. So two positive extremes and one negative extreme makes it as 3B and 1G graph. So this happens when the impedance vector is flowing between plus 45 and 0 degree. So similarly, when it flows between 0 and minus 45, both the components starts notching around, but you can see that the G notches much later than the B. So you have 1, 2, 3, so you have 3B, 3G graph. So the 3B, 3G pattern is obtained typically when the impedance vector is flowing between 0 and minus 45. So similarly, when it is closing when the impedance vector is flowing very close to the mass component or mass quadrant, mass axis, so that is between minus 45 and minus 45 and minus 90. So then what you get is a pretty complex notching for the B graph. That is, you have 1, 2, 3, 4, 5. So that is, you have 5B3G. So whenever you get a 5B3G pattern, it actually indicates that the impedance vector is flowing very close to the mass axis. Okay. Yeah, coming on to the important question, why there is a notch in the tympanogram. So as you know, we are measuring in a routine tympanogram, single component tympanogram. What I mean, what we measure usually in clinics, actually what are we measuring? We are measuring pressure in the x-axis and the amplitude of compliance in one axis or in y-axis. So this graph, this units here, actually they are the quantity or the extent or the what is the unit for compliance change, which is nothing but BS alone. So that is the single component tympanometry I showed you in the previous graph. In a multi-component tympanometry, we are not measuring BS, we are measuring B total. So I told you that in the previous slide, this graph actually represents BT. So that is combination of minus BM plus BS. And a notch in this particular graph. Typically, this notching happens around the static pressure, that is the static mid-layer pressure. So at that particular pressure, the contribution by B is less. So that is why it notches. Why not there is a decreased contribution by B in other pressures? Because actually we are either increasing or decreasing the pressure, or pressure is relatively increased or decreased with respect to the zero or the static pressure. In this graph, we are inducing additional pressure to the tympanic membrane by artificially biasing it as a stiffness dominant system. Whereas very close to the zero axis or very close to the zero static pressure, what you actually see is the static characteristics or the original characteristics of the middle ear. Okay, so this is similar to 1B 1G pattern. So you are seeing a B graph which is getting notched. So you know when does a B graph notch? B graph notches somewhere here, right? B graph notches somewhere here. In a normal middle ear happens around 1000 hertz. So that means, right, there's the contribution by B component at that particular static pressure is less. But I've shown here different type of notches, so you can see that then this also could be a notch, this also could be a notch, this is also could be a notch. So what we considered as a notch, actually the typical occurrence of notch itself indicates that the impedance vector is not flowing close to stiffness axis, it is flowing far from the stiffness axis. So that is a general interpretation. But specific interpretation, the depth of the notch, if it is equal to, if the depth of the notch, if it is equal to the tail values, that means almost no compliance by the mid layer. Okay, so then we can consider this mid layer system is under resonance. That is this portion. So that means BS and BM, they got completely cancelled against each other. So there is absolutely no compliance. So that's why the tail value is equal to the notch value. Okay, so whereas this could be somewhere here. So that means there is an increased mass component, but then still the mid layer or the at that particular frequency, the mid layer did not reach resonance. So this typically happens when you when the mid layer is the impedance vector is flowing very close to the mass axis, mass quadrant. So did you get it? Okay. To summarize, so you have notch in the tympanogram, which is actually an indication that it is yeah. So notch typically indicates that the impedance vector is not flowing very close to the stiffness axis, and the different patterns of notch. So when there is a small notch, it is indicative that it is flowing not very far from the stiffness axis. It is still far from the stiffness axis compared to the normal mid layer. In this case, it is close to zero, where the contribution by B is almost nil, because the amplitude at the notch is equal to the tail values. That means almost no compliance. So in this case, it is flowing in the negative direction. That means the total impedance is very close to the mass axis. So that is about notches, and that is about patterns. So how to use this to interpret in a clinical situation? So let us imagine that in a routine clinical situation, we would have heard about D-type and E-type tympanograms. So that usually comes in, you know, that it is in pinhole perforation. So where there is mass domination, or there is mass dominant, typically you get notched pattern even in infants. When you do, actually you are doing it for 226 hertz probe tone, but there is a notch. So that is an important factor. So how do we interpret in that case? So if there is a, but you have a notch in the tympanogram, that simply means that the stiffness component is far reduced. That is, as you saw, it would take 1000 hertz for the BT to become equal to 0. That means when you are presenting 226 hertz probe tone itself, the impedance vector is not here, rather here. So what does that mean? A mass dominated mid layer. So that's why you get AD type. Sorry, D and E type. Okay, so that is in normal tympanogram. So let us use this Van House model and explain some at least two cases, two extreme cases. Okay, so let us imagine a completely stiffness dominated system where there is ossicles are completely stiffened and it is locked against each other so that they are not moving. The tympanic membrane become extremely stiff, right? Okay, so now in that case, this vector is flowing not here. In fact, it is attached very close to the 226 hertz or the stiffness axis. Even if you increase the frequency, that is not allowing the impedance vector still doesn't come very close to the means it doesn't change as in the normal case. Rather, it changes very slowly. You can imagine somewhat like the impedance vector in a very stiffness dominant system is like this. It actually is not possible, but I'm thinking, means I'm just for sake of understanding. So it would take 1000 hertz. Even at 1000 hertz, you would find impedance vector still flowing here. So that's what happens. Even at 1000 hertz, if you get 1B 1G pattern, that is an indication that the system is stiffness dominated. Whereas in a mass dominated system, what actually happens is even at 226 hertz, the impedance is flowing here, impedance vector is flowing here, somewhere here, and when you increase to 1000 hertz, actually it starts flowing here. So you get 1B 1G pattern even at 226 hertz, and you get 5B 3G pattern at even 1000 hertz itself. You will get start getting 5B 3G pattern. So that is an indication of mass dominant pathology. So that is how we find out, and that is how we use Van House model to figure out whether the system is mass dominant or stiffness dominant pathology.